Right, yes, they are. Exactly. And somebody already said that they are not positive. Yeah. How do we see this? We can just take where is it? Sorry. I'll show you. Yeah, like why is it the case? Exactly because the derivative is positive. The first derivative is positive, and then we would say that that is why we have positive marginal returns. However, if we look at the second derivative, we cannot say it's exactly it's equal to 0. We cannot say it's decreasing marginal returns, or we cannot say it's increasing too, because it's equal to 0. So marginal returns are actually constant here, yeah? Like they're always equal to what, to a, and it's linear function, so we kind of cannot do anything about it. And this alone kind of violates this requirement of the neoclassical function. So we say, all right, not neoclassical. And then in other conditions, I also not fulfilled, because if we take marginal products, we'll see that they're constant and they don't approach 0 or infinity, regardless what L is, because marginal returns are actually independent from L, from our level of inputs. All right, we're done with this. We're done with this A function. What about B? Does it have constant returns to scale? No, exactly. We cannot even say exactly. Oh, this was the very, very nice answer to this. So basically, we know from the task that alpha plus beta is not equal to 1. And then if we multiply both inputs, we have to multiply both. That's kind of important. Yes, not just one, but both by some constant. I just took constant b. Yeah, just like the first letter I could think of. If we multiply both inputs by this letter b, we see that it should be the same as multiplying the whole output by this letter b. This is what constitutes the constant returns to scale. Here we see that if we multiply capital and labor by b, so we take it out of these brackets, we have b to the power of alpha plus beta. And this is not equal to b, because here, like whatever value b takes, it actually only because b is not equal to 1, because like if it's equal to 1, it's like then we don't increase inputs, like then we keep them constant. However, for everything else different from what? Whatever this power is, we know it's not equal to 1. And if we put b to the power of not equal to 1, then we just say like, all right, this is definitely different from b. That's the point here. And the rest is of course equal to y. However, it's not the same as saying like it's b times y. No, something else. So we can go on. Marginal returns. Marginal returns, are they positive? All right, they're positive. That's good. are they diminishing? Right, they are not. Right. Yes. First derivative is bigger than 0. Second derivative is actually we can't say if it's bigger than 0 or not. We need more information about. So we need to know what alpha is actually is. So first derivative is positive for sure. Alpha is bigger than 0. That's what we know. The rest is kind of positive. For the second derivative, can be both positive, negative, we don't know. Yeah, because if alpha is bigger than 1, then the whole derivative will be bigger than 0, and we will so we need to know if A and B are greater than 1 of them. Yes, here in this case, we have to make sure that like we can see the sign of the second derivative. Yeah, like with this information that we have about alpha and beta, we cannot say anything. We cannot say that like if alpha minus 1 is bigger than 1, or is bigger than 0, or smaller than 0. Yeah? Like if alpha is bigger than 1, then this whole thing will be positive. We have increase in marginal return. If alpha is smaller than 1 and bigger than 0, yeah, then we have diminishing marginal returns, then it's fine. So here we cannot be certain. And yeah, this is like kind of in this task I didn't really put information about alpha and beta because we don't need it anymore. We know that alpha we know that it's not neoclassical function. Yeah, so like then it's kind of alpha, beta, it doesn't really matter because we know it failed on the first condition, then it's kind of, we can just forget about it. The same actually holds here. Well, I mean, it depends on like the assumptions of the model. Yes? What function you want to see. Then in other conditions here, will be, we also don't know if they're fulfilled. We know that it also depends on alpha. If alpha is bigger than 1, then in other conditions are not fulfilled. If they are fulfilled, then it's, if alpha is smaller than 1, then they are fulfilled, then it's kind of all right. Right, coming back to our third function. Third function, which is E here. Yes, exactly. It's constant. It's constantly tends to scale. And now we can just go on with like this over to see why is it the case. So here we multiply both parts, both inputs, by some constant c. Yeah, like some number. C, we multiply k, we multiply L by this amount, and then we just take c out of brackets and see like it's c to the power of alpha plus 1 minus alpha. And it's equal to 1. Yeah. And the rest is just our output. Yeah, like it's k alpha to the k to the power of alpha times al to the power of 1 minus alpha. That's good. We see that this is just c times y. Our constant returns to scale are something like requirement is fulfilled. So what about marginal returns? All right, marginal returns are positive. All right. That's the correct answer. They're positive. We just take derivative of this function and see like everything alpha. We know alpha is bigger than 0. Al, k, positive, and then regardless which power we put them, they always will remain positive. That's good. The second derivative, like the first part of this expression is just a constant for k, so like that's why we take it. We take it as it is, and then we say like the derivative of the rest is alpha minus 1, which is negative, k to the power of alpha minus 2. It has to be actually alpha minus 2, not minus 1. However, it doesn't matter what power it is, because k is positive. Regardless what power it is, it will always be positive. So we have three positive characters, one negative. So the whole thing is negative. So we have positive and diminishing marginal returns. That's good. That's kind of that's our assumption. That's our requirement for this neoclassical function. That's good. Two are fulfilled so far. You could see that the same holds for L. Yeah, like we've done it for only K. Formally, we could also we have to be sure that K has the same kind of mechanics. Yes, diminution is the same as decreasing. All right, now we just say like the last thing is in other conditions. And to talk about in other conditions, we have to look at first derivative, and we can just reformulate it like as a fraction. It will be kind of easier for us. Al divided by k to the power of Al divided by k to the power of 1 minus alpha. We'll see what it means. That we look like how many times can I fit infinity into this marginal. How many times can we fit infinity into something finite? We cannot divide by infinity, but like we could imagine that we try. Yeah, of course we cannot fit infinity anywhere, so that's why it's 0. And how many zeros can we fit into some level of AL? Of course, like 0 doesn't take any space, so we can fit as many zeros in this thing, and that's why here it's infinity. All right, so they're fulfilled. So 3 out of 3. That means it's neoclassical function. Again, the same thing holds for L, for labor. And so now we can go on. We can just go to our task 3.2. And here we know that already this function is neoclassical. So the function we use now in the model is the same as function c. Here's the task sheet. So this function is the same as one in task 3.1c. However, there is a slight difference that a now is not just a parameter, it's not just a constant, it's another factor of production, yeah? Another input. And moreover, unlike the lecture, we also know that it grows at the rate g. Yeah, you remember at the lecture we said like, oh, we kind of don't care much about technology because it's constant and we can suppress it. Here we would actually say like, no, we cannot just suppress it because it also evolves over time, and we have to kind of acknowledge this fact. All right. This type of technology is called labor augmented, yeah, because it's first of all aims to increase to make labor more efficient. Of course, capital benefits from it too. However, the main kind of effect is targeted on labor. Yeah, that's why they have, like, for example, they have the same elasticity of output. What else? Yes, and the rest is kind of standard setting of the solo model. So we know that population grows, technology grows, capital depreciates. And to have new capital, or like to replace the old capital, individuals save a constant fraction of their income, or the total income. So basically, it doesn't matter how rich you are, you always save a particular fraction of it. Right, and now we have to write down the intensive form of production function per unit of effective labor and use it to derive the fundamental equation of the solo. All right, this fundamental equation is kind of important, but before we do this, we have to define what is effective labor. Yeah, so now we have not just per capita terms, but per unit of effective labor. That's a bit more advanced. It basically tells us that now we don't only care about the number of workers, but we also care about their quality. So we say like, all right, now we care about the technology the workers are endowed with. You can think about this as education years, for example, because it's hard to find some measure of technology. It's kind of weird. Measure technology in some units. So we say like, all right, it's number of education years, like a bit different, of course, to technology, but at the same time looks familiar and similar. And now we start with the task by just listing some notation. So like notation of the solo model and of my handwriting too. So yeah, on top we have this production function. So this is big Y, yeah, like big Y, capital Y, uppercase Y. Yeah, like we can call it many names, large Y, but it just like it means that this is like total output in the whole economy, which is a function of capital, aggregate capital, aggregate labor, and technology. This is the total output or like aggregate output. For hat will come in a second. For the hat we didn't do yet. So technology so like Y, big Y is the total output. As I said, like technology is hard to measure, so we can think about it as as the education, number of education years. Yeah. Alternatively, you can think about it as how many technological processes one worker knows, for example. Yes, A is technology. Right, and now we introduce new kind of human capital. Yeah, like there is this there is this paper by Mankiw, Roma, and Weil, and they did kind of one step forward with this solo model, and they introduced the human capital as the kind of as one thing, as one kind of factor. Additional one. Here it's a factor, but like it doesn't go outside labor. So it's labor augmenting technology. So it's for now we can think about it as human capital, something like this, as quality of workers. Yeah. However, it's not explicitly there. Yeah, skills. Number of employees is L. So this is number of employees, and skills. This is what we have here. This is like, because like this 1 over A, it's like the hierarchical model, and we'll come here now. We'll just we will use some substitution. We will use some substitution, so it will be fine. All right. Going back here, like to define this output per unit of effective labor. So like AL is effective labor. We introduce just new character Y hat, which means this is our output. So output per unit of effective labor. Yeah, so it's little y hat. Yeah, that's why we have hat on top, because we not only divided by L, but also by A. So for example, it's like the output per one worker endowed with 1 year of education. Yeah, if we take technology as education, this is output. And so this is just a definition. So like hat is not a mathematical operator. No, it's just a symbol to differentiate between simple y, little y, and per unit of effective labor. All right, if we divide this function by AL, we will see that this is the same as K alpha times AL minus alpha. No, not necessarily. We'll come to this in the end. But no, technology is good. Yeah, so like you can look here and say, see, yeah, for example, the more technology we have, the larger is the total output. And even more, if we look at this yes, the less is y hat, exactly. However, maybe it's not so important that y hat is little. What I mean by this is it tells us how much 1 year of education of one worker is rewarded with. Yeah, and for example, maybe you don't care about that much about how much each of your education year is rewarded, because in the end, what you care about is as an individual in this little y without head. Yeah, because here we just say like, all right, this is what basically our salary is as an individual. Yeah, like of course then you would like to have more premium for your skills, but it's not kind of super necessary here. So then we transform production function in units of effective labor. Yeah, it's the same, we just transform it further, and here we have like, all right, K, big K, like capital overall, the aggregate capital in the whole economy per unit of effective labor. This is like this big thing, and we see like, all right, this is like something familiar. This is capital per unit of effective labor. So why don't we just substitute it with like little k hat? Yeah, the same intuition as with y hat, and this is a function which determines our y hat. So we have to not forget alpha. So and I see like that alpha, sorry, that y hat is a very simple function of k hat. It's not r hat, it's k hat. Little k hat. With an alpha. Yeah, so it's just substitution. So basically everything that we divide by AL becomes like per unit of effective labor. So A is technology and AL is effective labor. So it's not just raw labor, not just one worker, but it's also like kind of skills that one worker has, so to say. Yeah. So here, for example, we see how much capital one worker has given his level of skills. Yeah. So for example, maybe it's for example, imagine you go to work in the fields and you are given some machine, but you're given a plow, you know, like this heavy thing to dig soil. Can be powered by like animals or like some machine, but it's like a heavy big thing which digs the soil, and it's capital. Yeah, and your capital labor ratio in this situation is kind of high. Yes, like capital per capita, per person, it's high. It means that there is also A in the denominator. Yeah, so you can think about this as little means per capita with a hat per times technology. Yeah, so like, yeah, so we can read this like, all right, if it's little, it's per unit of labor. And if we see the hat, we see like, oh, it's not just labor, it's effective labor. All right. We go on. And now we see like, we go back to our field. Yeah, so maybe capital labor ratio, if you have a plow, is high. However, this doesn't kind of consider your skills. Your skills are probably high enough to do something more sophisticated than just working in the field and growing potatoes with a plow. Yeah, your capital per unit of effective labor, so accounting for your knowledge, is actually quite low, because like flow it's a cool instrument, but you need something more sophisticated to fully kind of reveal your potential. So you might need like a computer with internet, which is like one computer is cheap, but like with the access to the internet, it's kind of the big thing. It's kind of quite an expensive stuff. So it's A in the denominator means that we consider not only the number of workers, but also their skills. So like how much capital for worker over a particular skill level, how much it gets. All right, this is notation. Yeah, so this is notation. And now we have to find how does this little k hat evolves over time. We know how capital K, or better say uppercase K, or big K, large K, total capital in the whole economy. We know how it evolves. Yes, like the dot on top means change over time. Yeah, don't confuse it with the growth rate, because growth rate is the time change divided by level. Yeah, so it's basically how many new machines we get per year divided by K. It's like the how many machines we had already. And we know that like we get new capital from investments, and the old capital gets kind of depreciated. So like this is depreciation rate times K. So like basically tells us what share of old machines can get broken. And we know that we assume in the solar model that everything that we save, we invest. And the opposite, yeah? Like everything that we invest was saved inside this country. Why is it important? It's important to show it that we have no other sources of to kind of use money either than saving or consumption, and we also cannot take investments from anywhere else. So investments are kind of directly linked to our productivity domestically. And this is depreciation. Right, now we cannot just divide this K hat, this K dot, big K dot by AL. This is not what we need, because we know that AL also evolve over time. It's like they also change. That's why we need something else. So basically, we need to find out the K hat, little K hat with a dot. So we need to find the time evolution of capital per unit of effective labor. This is our task here. This is the task of solar model. That's what we will look at now. So what is this little k with a hat and the dot on top? This is our capital per unit of effective labor. Now this is what it is. And we want to know how it evolves over time. So to do this, we just take time derivative of this little k hat and see what comes out of it. We know that little k hat is the same as k divided by L. So we take time derivative of this thing and see what comes kind of out of this. Yes, it's a closed economy. So like there is no international trade, no capital mobility. That's the kind of big assumption of the solar model. Later we can actually see why, how can we kind of relax this assumption and what happens if we do something else. It's like what happens if we allow for example, for flow capital. However, this is more already the macro course. Like here we will focus on this closed economy because it helps us to analyze these effects that we are kind of interested in the development course. All right. Take derivative of this fraction. We need to use chain rule, quotient rule, product rule, these three kind of rules of derivation, which you know from the school program. Yeah. K dot is the time derivative of a value of this capital. L dot is the time derivative of labor. A dot is the time derivative of technology. Now we know that we have to kind of this more. So this is kind of this big and complicated, not complicated, but like a bit big expression. So because we have to take derivative of a fraction, and in the denominator we have also like the product. Previous row, why is it not I dot? Yeah, so like here investment is just like kind of a flow of money in this particular time. Yeah, so like the I dot would be like change of investments. Yes, like it's not the stock of capital. No, it's just the flow of new capital. Yeah, so the same. So this is like how many new machines we purchase, and this shows us how many old machines get broken. Yeah, so it's investment in period T. Right, and then we can just start simplifying this equation. A depends on time. Yeah, so A changes over time, and we know that it grows at the rate G. So the task tells us that A is also a time changing factor. We can't say it's a function of something. We don't know how it grows, so it's kind of exogenously given to us. Yeah, we just take it as it is. And then we start opening the brackets, simplifying terms, and so on. Yeah, so like, and then we simplify things, cancel something out, and then in the end, we just slowly approach to something really more interpretable. Because we say like, oh, this is L dot divided by L, and A dot divided by A. This is something we know. These are the growth rates. Yeah, the growth rate of population, growth rate of technology. All right, this is already kind of helpful. We go on. So like we just rewrite it in this form. And then we say like, all right, I know what K dot is. So why don't I use it? And then we just put it here. Put it here and see what happens. So we look at this fraction and say like, oh, this is a big Y divided by L. This is our Y hat. A divided by AL is our little k hat. So again, things we know. So here it's the same KL, yeah, it's like little k hat. So then we just write it in this form, and in the end, we get the fundamental equation of the Solomon. So basically, it's it's an equation that shows us in kind of static terms how capital per unit effective labor evolves. Yeah, remember, this whole kind of sequence, this whole sequence of equations. Oh, sorry. So this sequence of equations is here to show us how this little k hat with a dot, so how capital per unit effective labor evolves over time. Yes, N is the population growth rate. Oh, labor growth rate, yeah, it's the same. And here we have to interpret this equation. So it's basically, we see two, yes, I will send you the sheet. It shows us how do we accumulate new capital. So it basically gives us sources of new capital. This is the first thing here. And the second thing tells us how can we, what decreases the capital level per unit of effective labor, which factors drive it down. With the first thing, it's super easy. So per unit of effective labor, we save some given amount of output per unit of effective labor. And this is what we invest. That's easy to understand. With the second term, it's a bit like we aggregate here several effects. Let's start with the depreciation. This is easy. Yeah? The more capital we have, so depreciation is just like it was given to us from the task from the very beginning, so we know that from here, yeah, that capital depreciates. We get it from the k dot, from the big k dot. And then when we know that k has to evolve, so basically it's kind of natural evolution of capital alone. Yeah, like what happens to capital, not to labor and technology, as this n plus g. Yeah. So we see that the more capital we have, the more gets depreciated. Yeah, so that's easy to understand. Yeah, so to imagine, because yeah, like if we have a large factory with like complex machines, of course you have to invest a lot to maintain them, yeah, because you kind of have to repair them, clean, whatever you do with big machines. All right, the n plus g are not so a bit less intuitive. Let's start with n. So n tells us that if we have more workers, if our amount of workers increases, our capital per unit of effective labor, or just per unit of labor as well, decreases. Yeah, so because, of course, the more workers you have, the more people have to share the capital that's already there in the model. G is the technology growth rate. So it basically tells us that if we remember, we had this example at the lecture of a factory where people assemble phones, yeah, and each one has a screwdriver. If somebody goes to this factory, new person kind of gets employed. You have to give him a screwdriver to kind of make him efficient. Otherwise, your capital labor ratio will go down because you'll have more workers than you have capital. So basically, it tells us that to keep capital per unit of effective labor constant, we need to endow new workers with the same amount of capital as their kind of parents. Yeah, in the scope of the whole economy, it tells us that basically, if new children are born, they also kind of want their share of existing capital. So that's why you have two options. This is a very good example with dynasties. I think you already had these dynasties in some other courses. So like dynasty as a family, like as a household, kind of, you have your parents, then you are their kids, then you have your parents. So like this is kind of going on as a dynasty. So Russian dynasties is a perfect example, yeah, like because normally people in Russia live with their parents until a certain age, and then comes the question what to do with the flats. Yeah, and like the oldest child gets so parents, like gather all things in the flat to sell them, and then finally to buy a small flat to the oldest kid, and to the kind of youngest kid, they leave this person their own flat. So yeah, like at some point when these people kind of die, the flat gets free, and the youngest kid has the flat of the parents. The oldest kid bought kind of his own flat with the help of the parents. Yeah, bit long example, but to show that here basically not to decrease the capital per number of kids, you need to buy a new flat. So you need to accumulate new capital to keep the capital labor ratio constant. G also has a negative effect on capital per unit effective labor effect. Yeah, that's not so intuitive on the first glance. However, if you think about this, it makes sense because it tells us that if your workers become smarter, fast, so like G is the growth rate of technology, so like the higher the G, the faster they accumulate knowledge. It tells us basically that you need to provide them with more and more capital so that they can keep being efficient. Yeah, imagine if you work in the you're doing some like programming, yeah, like now you can have a normal laptop. Then if you get more kind of educated in this area, now you probably need this, like the Apple laptop already, yeah, like maybe Windows laptop will be not enough. So you need to provide your workers with more and more capital. At some point, people require quantum computers to kind of keep efficient. So that's why if technology grows fast enough and faster than, for example, you accumulate your new capital, it comes to the point where your skills kind of start exceeding the level of your capital. Yeah, so like there is some capital, there is some computer, but you cannot work efficiently there because you're kind of too fast, too smart for that. All right. And this is it about the fundamental equation of the Solow model. So we, to sum it up, we see that this is accumulation of the new capital. This is like ways to dilute. So dilute is like from M and G, and kind of deplete is through depreciation. All right. Now we go to the task B of the task sheet. We have to draw the Solow diagram. And we have to see what happens to the output, capital per unit of effective labor. We need to assume that we're in the steady state. So, who remembers what steady state is? Exactly. Exactly when like little k hat in this case, or before we had like just little k equal to 0. We put star to note to define it as a steady state level of capital. Yes, like if you have star next to the k or next to the k hat, it means that its evolution is equal to 0. Yeah, so like it's the dot of k or dot of so if it's dot over k hat is equal to 0. Why isn't it? So I don't get the question. So can you reformulate it, please? From G. I still don't get it. Could you please reformulate it? So we'll come to this like once again. So basically, G here tells us how much new capital you need to keep your workers with the particular level of knowledge, so like with a particular, say, length of education. So it tells you how much capital you have to provide them new, corresponding to their level of, to the increase of skills. All right. Yes. So in the steady state, we know that the capital per unit of labor, or effective labor in this case, is constant. So like this k hat with a dot is equal to 0. And the steady state level of capital, so like this is the time change, it's equal to 0. But the k hat without the dot, yeah, like if we kind of forget about the dot, k hat is not equal to 0. It's some given level of capital. All right. And now, if we look at the task, we see that now we have a decrease in technology growth rate. So like technology grows slower now compared to the past. If we look at this fundamental equation, we can see that these are kind of two separate lines. This line is a curve because we know that alpha is the function of k hat. Y hat is the function of k hat. So just k hat to the power of alpha. So here it is, yeah. Y hat equal to k hat to the power of alpha. It's a curve. Yeah, you can easily imagine this. Well, this thing is linear in k hat. Yeah, like just like k hat times some 3 constants. That's a straight line. Of course, if we have such a setting, we know that these two lines intersect only twice. One is when everything is equal to 0. This is the corner solution, and this is not something we're interested in. Like, yeah. everything is equal to 0, maybe it's not so fun to analyze. However, we know that afterwards, both are monotonous. Like both functions are only increasing. So they intersect only once, and then they go then they diverge. If we look at this function, at k times n plus g plus delta, the decrease in g, how does it affect the slope of this line? Does it become flatter or steeper? So like flatter means it rotates clockwise, steeper means it rotates counterclockwise, or it becomes more parallel to x-axis or more parallel to y-axis. Which one happens here? If g goes down, exactly. No, it becomes flatter. It becomes actually flatter. I'll show you how it looks on the graph. So this is our solo diagram. And solo diagram plots the output as the function of capital. Capital per unit of effective labor. Yeah. So on the y-axis, we have output. Yes, exactly. If we decrease output, if we have output here, we'll also see that we can measure investments in terms of output. Yes, like this is basically to measure these lines, but given that our investments are expressed in as a share of output in output units, we can also do this for capital depletion. Yeah, so for this line. So, and then here we see that the black line, this is just the function of k hat. So this is our little y hat. So this is our output per unit of effective labor. And we see like the more capital this unit of effective labor has, the more we produce. Yeah? It's quite simple. That's okay. The more capital you have, you can use, the more efficient you become. Of course, at some point, like becomes too much capital, and you don't benefit from it much or at all. At some point, if k approaches infinity, you remember, marginal product of capital will become 0. Yeah, but we see that it never harms to have too much capital. That's for sure. And here we basically see that the blue line is linear transformation of the output. So we take this non-linear thing and linearly transform it to the blue line. So it's just the share of the black line. So basically everything below the black line is the output per unit effective labor. Everything below the blue line is the savings, which is the same as investment. What's the difference between the black and blue line? So in between here, what can we see? What is this? Consumption, exactly. So this is consumption here. And here we can see what happens to our k dot in different sides. So we know that this intersection here is the steady state. Yeah, so this is the steady state where savings and investment are equal this capital depletion. So this is what we have here. To the left of the steady state, we have capital accumulation, yeah, because we know that the savings level is above this black line, the straight black line. So basically we know that we save more than is needed to compensate depreciation, growth of technology, growth of population. So basically here we know that our workers become they gain capital every instance of time. They get more and more machines, so they become more and more efficient. At some point they'll probably reach the steady state, and in this steady state economy is not stagnating. Like the wrong way to see it. It means that here your capital per unit effective labor is constant. However, it means that basically new workers, new generations can have the same level of capital as their ancestors. Also per unit of the knowledge. So like basically here we get more people, they become smarter, and per unit of effective labor, so like given their level of knowledge, they get kind of the same level of capital as kind of from the past. So it means that they kind of, in aggregate terms, here we know that the economy grows actually at this rate, n plus g plus delta. So in aggregate terms, we know that in this point in the steady state, our economy grows fast enough to fulfill three basically purposes. First of all, to feed new people, so newborns, to compensate them kind of adequately, to provide them with capital that is enough for their growing knowledge. So capital is actually become more and more sophisticated, and it's also like enough to substitute old machines, to repair the old machines. So here is actually a lot going on, even though the k hat with the dot is equal to 0. And on the right of this part, we see that this capital depletion actually exceeds capital accumulation. So more capital gets wasted than capital gets accumulated. And here, naturally, the economy kind of converges to this steady state. All right, this is how we read the graph. And now we know that like if our technology growth rate and of the chart up you mean this line? So like no, if we want to make the line kind of steeper, all the lines. All right. It's just a production technology here. So this is how technology looks like. Yeah. So basically, it assumes that to have this like blue line or the black line to shift them upwards, we cannot do this. Yeah. So we cannot do this. We just have to accumulate new capital and that will make, like, we'll move along the line, and so we can move further to the right. This is the purpose of the solo model. Yeah, so we assume basically that, of course, we could also have of course, we can make this Cobb-Douglas function, enrich it with like something like another level of technology, like another kind of technological parameter. However, maybe we don't need it, because what we focus on is that basically on this capital accumulation, because we believe that no country yet has reached a steady state. So like all countries accumulate capital. Some countries are close to it, like closer. That's why they grow slower. So developed countries. Developing countries are kind of far. That's why they can kind of converge faster. Yeah, to have like this parallel shift of the graphs, we kind of don't. We don't expect it, so to say. Like we don't need it. We just say like that. All right, we need to have more capital, then we'll become richer, and we'll increase our output. So I also, you see, like I also draw it this way, so like we have only like minor shifts. However, if we like think that like developing countries are somewhere here, the lower part, then like increase in capital stock will actually increase the life dramatically. Yeah, like you can see big improvements in the lives. However, if our speed of technology, our growth of technology slows down, you see that the steady state actually moves to the right. Now, this is not super intuitive, because what we see here is that now basically we still accumulate knowledge, but slower, and it means that like this steady state, the steady state will have a larger capital level per unit of effective labor. To have it like to bring more intuition here, we can think about it as, right, it means here in this point that like if your workers become they accumulate knowledge slower, they will be easier to impress. Yeah, imagine that you go to like a super cool programmer and tell him, we give you a laptop. So for example, I have this normal Dell laptop. Yeah, like it's normal Windows laptop. It's actually older than 5 years old, and probably the programmer, like this cool IT guy, will say like, all right, it's not so much of a capital for my level of knowledge. Yeah. However, for my level of computer knowledge, that's totally enough. Yeah, like I don't need it for like some complicated programs. I don't need like a MacBook. So for me, this level of capital is actually higher, because I find it like it kind of matches my efficiency completely. So for me, given my, so to say, like poor level of technology, this capital is, the level of this capital is higher, while for his level of knowledge, this level of capital is not so great. So he needs a super cool laptop. And that's why we see that we slowly start converging here to this point, meaning that like we will accumulate new capital, but not as not in only aggregate terms, but more in these terms per unit of effective labor. So we'll be more endowed with capital per unit of effective labor, but not in other, so like per unit of effective labor, period. That's it. And once again, we see that in the steady state, we are, you remember from the lecture, we are on the balanced growth path. So economy is still growing. It grows, but at a particular rate. Yeah, like the rate of n plus g plus delta. It's still good because if we look at per capita terms, because yeah, like as I told you in the beginning, we probably don't care about how many years of education are rewarded per worker. Yeah, like that's not important, because in the end, all salary for these education years goes to one person who has them. Yeah, and then at this point, for example, we see that per capita income or per capita level of capital grow. They do grow at the level of G plus delta. Yeah, delta is kind of needed to repair the capital, but here people are still getting better off, even though that we have more people, but they are getting better off because the technology develops. Yeah, so this is maybe this is something to think about, like in like for example, what you can see in Russia. Yeah, like for example, that's a bad example. It's very cynical, but all right. Let's say like we now, newer generations. Oh, that's bad, but all right. You see what I mean? We live better than our grandparents now. Yeah, like our parents live better than our grandparents simply because we have more human capital. Yeah, like we have higher level of technology. That's why our kind of per capita income is increasing. Yeah, because we know more things. Yeah, like generally, yeah, like when our grandparents were going to school, they were like, they didn't know how to use computers because there were no computers. Yeah, now we know this thing is kind of different. So our human capital, so like say your human capital is probably higher, will be higher when you finish your education than mine, because yeah, in between our graduation years there was something like you invented and so on. So steady state is not a bad thing, it's actually a good thing. It means that we kind of achieved such a point when we develop, our economy develops, it grows, but at a particular rate, at a rate enough to compensate for increase in population, growth of technology, and compensate for depreciation. That's basically it. All right, that's all I wanted to tell you today. Thank you very much for your attention, participation. Do you have any questions? All right, there's no questions, then or points for today, I have to calculate them because you were like super active. I have to look now through this chat and like mark it down who did what. I will upload the grades today or tomorrow, like all grades, like the test, the first two tutorials, like tutorial today and the previous one, and you will be able to see them in the March table. Yes, it's all about the closed economy. Yes, I will email them the Google link to the table. All right, and I'll also give you some, and by the way, next time we start with data. So please get it somewhere. It will be easier for you to follow. This. Yeah, so we have a closed economy. It's just easier to see this. However, it's more like already the macro question. If you want to have like international capital mobility, you can have it also in the solar model. It perfectly works. Just here, we want to focus on these kind of drivers of development inside the country. and not kind of between countries. So we want to say that why some countries are poor, some are rich, and international capital mobility is more about it's. For example, I teach it in my open economy macro international finance course. That's where I do this open economy of the solo model. So here we just want to focus on these particular things. And next lecture we'll talk why we needed it. All right. Thank you very much, and see you next week.